We'll now talk about isosceles triangles and the SSS congruence criteria. A triangle with two congruent sides is known as an isosceles triangle. The two congruent sides are known as the legs of the triangle. The remaining side is known as the base of the triangle. The angles opposite the legs are known as the base angles. And the angle opposite the base is known as the vertex angle. So if I draw an isosceles triangle, we have the congruent sides of the legs. So the other side would be called the base. These are our base angles opposite the legs. And this one up here is the vertex angle. We're now going to look at the isosceles triangle theorem that says if two sides are congruent, the angles opposite are congruent, and conversely. So if we know the two sides are congruent, then those opposite angles are congruent, and if those angles are congruent, then the sides are also congruent. So let's consider these two triangles ABC and ACB. So essentially I'll have the same triangle repeated twice. Because this is isosceles, I know that side AB is congruent to AC. Same thing, side AC is congruent to side AB. And I know that angle A is congruent to angle A. So I have side angle side. This gives me that triangle ABC is congruent to triangle ACB, which then tells me that angle B needs to be congruent to angle C, which is exactly what I needed. To go the other way, we will assume that our two angles are congruent, and this time we can use the ASA congruence criterion to actually get that the two sides are equal. Before I can prove my next big result, I need a preliminary result that says if B is in the interior of triangle ABC, then either the distance between P and A is not equal to the distance between C and A, or the distance between P and B is not equal to the distance between C and B, or both. So let's suppose they're both true. Let's suppose that PA is equal to CA and PB is equal to CB, and hopefully we'll get a contradiction. Since P is an interior point of the triangle, we know it's an interior point of all three of the angles of the triangle. Then we know that rays CP will meet our side AB at some interior point W. So here's a quick diagram of what we have right now. I have this triangle ABC. I drew the ray CP, and P is right here at this point, intersected with segment AB and got W. And I know that PA is equal to CA. So I know these two sides are congruent. And PB is equal to CB. So those two sides are congruent. There are 6 angles here that I'm going to be concerned with, which I've numbered 1 through 6. I can see that angle ACB is equal to angle 1 plus angle 2. By the isosceles triangle theorem, that tells me that angle 1 is equal to angle 3 and angle 2 is equal to angle 4. So this is also angle 3 plus angle 4. I can then rewrite that as angle 3 is 180 minus angle 5, and angle 4 is 180 minus angle 6. Simplifying gives me that that's 360 minus angle 5 plus angle 6, which gives me 360 minus the measure of angle APB. However, I know all angle measures are less than 180, so I have 360 minus something that's less than 180. Which is greater than 180. So now I have that angle ACB is greater than 180. And that's going to cause a contradiction. So at least one of these two things has to be false. We can now prove the SSS congruence criterion. This condition says that if 3 sides of one triangle are congruent with 3 sides of another triangle, then the two triangles are congruent. Let's suppose we have that AB equal to XY BC is equal to YZ and AC is equal to XZ. So we have all three sides of two triangles are congruent. If any of the angles are congruent, then I have enough to satisfy my SAS postulate. So we're going to assume that all of the angles are different. So we're going to suppose the measure of angle X is smaller than the measure of angle A and the measure of angle Y is smaller than the measure of angle B. Inside of our angle CAB, we're going to construct a point U so that angle UAB is equivalent to X. And within CBA, we'll construct a point V so that angle VBA is congruent to angle Y. So essentially, we're just going to draw these smaller angles inside of our bigger angles to be congruent to X and Y. In this case, the rays AU and BV must actually intersect at a point P that needs to be in the interior of the triangle since those two angles are smaller than the original triangle angles. By my ASA congruence criterion, triangle ABP is congruent to triangle XYZ. This would tell me that the segment PA has to be equivalent to ZX by the fact that these two triangles are congruent. And our hypothesis originally said that ZX is congruent to CA. Equivalently, we would have PB equal to ZY by these new two congruents, and then ZY was originally congruent to CB. But this gives us a contradiction to that preliminary result that we did before. Since P is on the interior, we have to have that either PA is not equal to CA or PB is not equal to CB, or both. So that gives us a contradiction, so our angles are congruent. Thus, we do have our congruence criterion.